Welcome, everyone. It's a pleasure to have Gokul Swami visiting us today from CMU. He works on the broad area of interactive decision-making, RL, imitation learning, things in between. I like in his description, he's interested in techniques for learning to make good decisions efficiently, even when good is hard to specify. And his work has had a lot of impact across robotics, language models, and the broader field of reinforcement learning and imitation learning. He's won a bunch of awards, including a teaching award, so hopefully he'll give us a great talk today. And so please take it away. It's a pleasure to have you.
Thanks. Hi, everyone. I want to start off by saying how happy I am to be here. I don't know if you guys noticed when I was setting up my slides, but my laptop background is a picture of Lake Kolchak. I did a hike there when I spent the summer in Seattle like 3 years ago here. I've dreamed about doing that hike again ever since. The other thing I want to say is I am super nervous, so there's a very high chance I'm going to say something that makes no sense in the middle of this talk. So if I say something and you have no idea what I said, please feel free to ask me quick clarification questions, but I'd appreciate if we would keep longer questions towards the end. Does that sound good? Okay, let's get into it. So today, I'd like to talk about how interactive learning can help us learn more from less. So broadly speaking, we live in incredible times, from robots that can perform complex bimanual dexterous manipulation tasks like coring this apple, to language models that can answer questions that require fusing together multiple sources of knowledge. Our decision-making agents have never been better. So if we peek under the hood of the way these systems are trained, the vast majority of data and computation is spent on supervised learning. So in the robotics context, we might collect data of someone controlling this robot to pick up this cup, and then train a model via regression to, conditioned on observations like the wrist camera image, predict the control torques the controller actually executed at that time step. Similarly, in the language modeling context, we might scrape a bunch of text off the internet and then train a transformer to condition on all the preceding text, predict the next token. So across these two different modalities, the training pipeline is surprisingly similar. We start with some sort of fixed data set, a sequence of state action pairs, and then train a decision-making policy that maps from the states in the offline data to the corresponding actions in the offline data. And while supervised learning has taken us far, our decision-making agents are still far from perfect. So I want you to pay attention to this cup here in the back. And you'll notice that after the robot fails to pick up the cup, it's going to get stuck in this loop of making the same failure over and over again, never actually recovering from this mistake. Similarly, if I ask this language model to evaluate a completely ridiculous business idea of selling berries to wild animals, it's going to tell me this is still somehow magically going to turn a profit, even though the animals do not have currency. Right. It seems empirically that even with an entire internet's worth of data, supervised learning wasn't enough to provide the performance and reliability we ultimately desire from our decision-making agents. So, to my mind at least, the most important question in decision-making is how we can learn more from less data. I believe the best answer to this question is to have our agents, whether they are robots or language models, interact with an environment and learn from this experience. This is usually called reinforcement learning, or RL for short. In reinforcement learning, agents collect their own data. Now, there are at least two things that make this hard. So let's imagine our agents start at the top of this tree and make a sequence of decisions, left or right, until they reach one of the leaf nodes. You can think of each of these decisions as an abstraction for something like a motor torque in the robotics context, or a token in the language modeling context. Let's say our agent needs to make a sequence of H decisions. The first problem is exploration, experiencing the right outcomes. So if we have to make a sequence of H decisions, the total number of outcomes we can see can grow exponentially with this task horizon and be ordered 2 to the H. So we can be forced to find a needle in an exponentially large haystack. The second problem is specification, knowing whether an outcome you experience is good or bad. So in contrast to something like a game of Go, where it's very clear whether an outcome is good or bad, you won or lost the game, specification is often complex in the robotics or language modeling context, as we have to deal with perception and nuanced user preferences. So my work focuses on addressing these two challenges, exploration and specification, in tandem. So whether it's applied to robots or language models, theoretical or practical, the heart of my work is in how we can learn to make good decisions efficiently, even when good is hard to specify. So in contrast to supervised learning approaches, where we'll start off with some sort of data and directly learn a decision-making policy, a lot of my techniques have a sort of two-step approach. So first, we will learn some sort of specification, a reward or objective function, in reinforcement learning terms, before solving the exploration problem it defines to back out a performant decision-making policy. And I've worked on both halves of this pipeline, exploration and specification, focusing on the translation of theory to practice. In exploration, I proposed the first polynomial interaction complexity imitation learning algorithms to provably learn recovery behavior and exponential speedup over prior techniques. We then applied these algorithms to teach robots to avoid nuanced contextual failures at test time. In specification, I proposed some of the first preference learning algorithms that are provably robust, the kind of conflicting feedback we often get from human or LLM judges. We then applied these algorithms to train language models to reason in lower resource languages, outperforming fully post-trained models that saw significantly more data. I've also spent time thinking about where and why the RL hammer is useful. I formalized the necessity of interaction for learning to recover from mistakes, as well as contributed to our core scientific understanding of why reinforcement learning allows us to learn more from less. Today, though, more than a broad picture, I just want to drill down on 3 parts of my work. The first is how we can learn performant policies via imitation without having to solve global exploration problems. The second is how we can extract specifications from conflicting preferences. And the third is, more fundamentally, beyond letting agents collect their own data, why reinforcement learning allows us to learn more from less. Let's start with imitation, and for this part of the talk, we're going to focus on the translation of theory to practice. So in imitation, our goal is to autonomously reproduce the behavior of an expert. So we can imagine having a person control this robot to pick up this cup, and we can view this as coming from an expert policy, pi e here in green. And our goal is to get the robot to be able to do the same thing without the person in the loop. I want to note here that I'm just assuming access to this demonstration data, so a sequence of observation action pairs, and no information about the underlying task reward function or the ability to interactively query the person for on-policy feedback. I also want to note this is a widely deployed paradigm, from Tesla self-driving cars to Waymo self-driving cars to Toyota Research Institute's robots. It's very hard for me to think of any robot learning system today that is not essentially trained via imitation. Okay, so how can we solve this problem? The easiest approach is to just treat it as supervised learning. It has a fancy name. It's called behavior cloning. All this really means, though, is we imagine breaking up our data into a sequence of state action pairs and training our policy, pi here in orange, to map from each observation, the image, to the corresponding motor torque in the data. And we can imagine doing this across our entire data set. Now, if this policy was perfect, we'd reproduce what we saw in the data. However, this is rarely true in practice. So let's bring in back our tree from earlier and imagine rolling out the learner's policy. So midway through task execution, we might make a mistake. And we might end up in a state where we haven't seen data before. We're then likely to make another mistake and potentially fail the task. And I derived strong lower bounds that establish that, in general, no offline supervised learning algorithm can learn recovery behavior. Intuitively, these are because if I only train on these green states, I can't tell how I'm going to do out of distribution because I'm just looking at how I did on this offline path. Okay, so what should we do about this? I think a pretty reasonable idea is to train a classifier between what the robot did and what we want the robot to do. So between the expert's green path here on the left and the learner's path here on the orange. We could then use the logits of this classifier as a reward function for a downstream reinforcement learning procedure. Now, after RL, we still might not have a perfect policy. So we can imagine iterating this process, training another classifier, until we eventually train a policy that reproduces the behavior of the expert. This sort of iterative process is called inverse reinforcement learning, or IRL for short. So more formally, we can view this process as game solving. So we're trying to find some policy pi that, regardless of the reward or objective function f we judge it under, exhibits similar performance to that of the expert, where jpif is RL notation for the cumulative performance of policy pi under objective function f. And I provided some of the first proofs that equilibria of this game learn recovery behavior, as they must be robust against the worst case verifier. So more mechanically, the outer loop of IRL is adversarially picking a reward function, while the inner loop is optimizing it via reinforcement learning. Now, while this approach has strong theoretical guarantees, actually doing it in practice is often practically quite challenging. So let's imagine the adversary chose the reward function, shown here in red. To compute pi star, the optimal policy of this problem, the learner might need to check every single leaf node to find this one in the bottom left. This means at the first iteration of this procedure, we've already had to pay exponentially in our task horizon. What's worse is that the next iteration of this procedure, the adversary is going to pick some reward function we look really bad under, and we're, again, going to have to solve a really hard exploration problem. So in some sense, it's like we're using a hammer of global exploration to try and stamp out all mistakes. This is a very expensive hammer to use. And I want to talk about how we can use a lighter weight hammer local exploration that will still be provably sufficient for learning good policies. So in particular, I'm going to bring in back the expert states here in green on the left. And we can imagine forming a local exploration procedure just in these states. So let's walk through this carefully. So the second to last time step, pi3 here, we have a single decision to make. Are we going to go left or are we going to go right? If we go left, we're going to get reward 1. If we go right, we get reward 0. So we choose to go left. We can imagine locking in this policy and then backing up a time step and saying, condition on me going left in the future, what should I do at this earlier step? So if I went left, I'd go left again, and I get reward 1. But if I went right, I go left again, and I get reward 0. So I would again choose to go left. So I can imagine locking in this policy and repeating this process all the way up the tree. So there are 8 steps of this procedure, because there's 8 levels in the tree. And at each step, I'm just doing a couple of rollouts from a state. So I'm paying linearly in the task horizon at each step. Thus, my overall interaction complexity is h squared, rather than exponential in terms of the task horizon. So I think the most natural question you might have at this point is like, okay, it's kind of nice that you picked green states and the adversary picked a reward function where the 1 is right on them, right? What if the adversary picked this reward function here, where the 1's here on the bottom right? Well, we're not going to actually compute pi star for this with a local search procedure, right? Because we're only looking at things on the left side of the tree, while the optimal policy here is on the right side of the tree. So I would argue that while this is true, it's not something we actually care about, right? This policy is visiting states that are completely different than the expert. So it's not actually reproducing the behavior of the expert. So the proof essentially formalizes the intuition that for imitation, we only need to compete against policies that visit similar states to that of the expert, and this allows us to reduce our search space and provides a computational speedup. So slightly more formally, what we can say is that after running T rounds of a local exploration procedure, we can compute policies that satisfy the following suboptimality bound, where pi bar is the trajectory level mixture of pi 1 through pi t, so the t policies we computed. The first term captures the misspecification of our policy class and is in general unavoidable. Second term captures our policy optimization error and can be driven down without extensive computation. And the third captures our reward optimization error and will be driven to 0 by any no-regret algorithm, which includes a wide variety of garden variety techniques like gradient descent. So put together, we've just walked through the first polynomial interaction complexity imitation learning algorithms that provably learn recovery behavior and exponential speedup over classical techniques. One thing I want to note here is that naively, these algorithms have an interaction complexity that's t times h squared, because we're doing t rounds of a procedure that's h squared. If you're a bit more clever about the way you collect data, you can reduce this down to just h cubed end to end. And I'm happy to talk about the details of that offline if anyone's curious. Yeah.
Apologies if I missed a bit. And I guess I don't understand how this is learning recovery behavior, whereas what we were looking at before wasn't.
Yeah.
I don't understand that distinction.
Right. So the idea here is that when I am running this local search algorithm, I'm observing the future consequences of what I would do after I take an action, right? So I know what will happen afterwards. So I can see that if I go like this, I'm actually going to go off the rails, versus if I go like that, I'm not going to. More formally, what you're doing here is game solving, but intuitively, that's what it is. Yeah. Other questions? Yeah.
When is recovery possible? Like, you could have a situation with a car where the car falls off a cliff, and I don't think you can do anything there. So, like, is there something about that that's captured here?
Yes.
Or,
Yes.
Yeah, how do you reason about that?
Yeah, I love that question. This question haunts me. So the purple term here basically captures, in some sense, how well you're able to recover from arbitrary mistakes. In general, for any of these interactive imitation algorithms to actually be able to recover from mistakes, some policy needs to be able to recover from mistakes. So when you have this sort of like walking along a cliff problems, you can't really recover from those, right? So there, it's really hard to actually, because there's no policy that can recover. What's distinct, though, is that sometimes, purely by looking at offline states, you can't tell whether the policy you chose does recover even when it is possible to recover. So these interactive approaches help tell between policies that recover and policies that don't when it's possible to do so. Yeah, so, right, so if I only evaluate my policy on some offline states, I never actually roll it out in the environment and see whether it recovers or not, right? Or see whether it makes mistakes or not, really, right? So with just that information, I can't tell whether policy recovers or not, right? However, if I actually roll things out and see what happens, I can tell good from bad. All right, so beyond just being a theoretical artifact, we can actually use these algorithms to train robots. And there's a couple steps it takes to do this, right? So I would maybe argue the core issue with the algorithm I just described is that you need to experience a failure in order to prevent it, right? In some sense, the robot needs to drop the cup in order to know to not drop the cup. Ideally, what we do is rather than recover from mistakes, we prevent making them in the first place. And to do this, we need to be able to predict the future consequences of our actions. So to do this, we're going to use the idea of a local world model or a learned partial simulator. It allows us to say that after executing a sequence of actions, this will be the consequence we actually observe in the environment. So to make this a bit more concrete, let's imagine there's 3 ways a robot could think about picking up this cup, which correspond to different sorts of grasps. What we're going to do is embed our observations, so our wrist camera and our joint angles, and we're going to forward simulate inside a model what's going to happen for each of these 3 different action trajectories. So these would correspond to things like failing to pick up the cup, picking up the cup but putting your finger inside the cup, and picking it up by the handle. Then, given this ability to evaluate or know the future consequences of our actions, we then need to be able to evaluate whether these are good or bad. The way we're going to do this is we're going to train a VLM, a vision language model, to describe these latent futures in natural language. So essentially what we're going to do is train a model to caption those videos you just saw. So this could correspond to saying that the robot fails to achieve a secure grasp, or the robot sees the cup through its interior, or the robot grasps the cup via the handle. We're then going to ask the same VLM to pick which of these is most aligned with what the user actually wanted, leveraging its common sense understanding capabilities. So for a particular task, maybe what we really want is pick up the cup by the handle. Let me walk through a kind of end-to-end version of this system now. So let's imagine our user asks us to serve a cup of water to a guest. This means we should grasp the cup by the handle rather than put our finger inside the cup and potentially contaminate the drink. And what we'll see is that the supervised learning algorithm here, trained on our data, is going to actually still often put its finger inside the cup. But by instead running this local exploration algorithm at test time, we're able to learn to actually pick up the cup by the handle and execute this more nuanced grasp that is aligned with user preferences. And we're able to achieve a much higher task success rate, even though we had access to the same data. For another example, maybe our user asks us to pick up a bag of chips without crushing them. This means we should pick up the bag by the edge rather than by the center and potentially crush the contents. So we're again going to see our base algorithm here, trained via supervised learning, is going to actually pick up the bag of chips by the center, while our local exploration algorithm is going to execute this more nuanced grasp of picking up things by the edge. And we're again going to get a much higher task success rate, even though we had access to the same data. We can also apply a very similar pipeline to deal with sort of finer-grained dexterous manipulation tasks rather than sort of higher-level mode selection. I'm happy to talk about the details of this offline, but the highest order bit is we see the same phenomena where even when given access, the same information, these interactive learning algorithms that learn all these different components are able to outperform the offline supervised learning algorithms. Yeah?
So I didn't quite understand the simulation part of it. So when you say world model, you're training like a model to generate video based on a set of videos that like the expert has created. Is that what you mean?
Yeah, essentially, right, yeah. So it's like action condition video generation, yeah.
And those videos are like pretty good and accurate, like simulator real world physics, or you have enough examples to be confident of that?
So I think they're accurate locally. So maybe for like a second or two, they're pretty good. But over longer horizons, things start to kind of fall apart. I'll talk a little bit about what I want to do about that in a bit. Yeah.
So, I mean, even these video models are trained from real world data. So, are you just offloading the tricky part about this failure data to like the data that was there for the video generation model? I mean, you're saying you want to prevent failures, but to actually be able to see those failures even in the video model, it should have been there in the data somewhere, right?
Yeah.
So
yeah, it's a reasonable question. So I think it's hard to get something for nothing, but I think that why I'm less concerned about data for video models is that in general, you can put a lot more data into them, right? Like we can put in multitask data. Sometimes things aren't failure, you just did something different, right? We can use play data and other things like this. So of course you do want your world model to, in some sense, have the ability to predict that when you do bad things, there are bad consequences. That's what the theory under here says a bit more formally. So you do need to have some data of failures, But ideally, you only need to fail once rather than fail repeatedly, right? You learn that this is a thing that can happen, and you don't do it again. Yeah. Good. Okay. All right. So I think your takeaway from this part of the talk should be that these sort of local exploration algorithms allow us to efficiently train robots to avoid failures. I want to note that more broadly, the algorithms and techniques I discussed here have become part of the standard analysis for imitation learning. They've been covered by classes at Stanford, Cornell, here, and CMU, beyond my own. They've also had sort of broader industry impacts. So one I find pretty cool is that the largest scale application of inverse reinforcement learning techniques in history was calculating the routes for Google Maps. And while there's a bunch of different moving parts in this system, one part of them was actually using these sort of local exploration algorithms. But I don't want to overclaim here, right? This is a huge systems project, but it's cool that these algorithms actually were one part of the largest scale application of these techniques in history. I also want to note that Matt Barnes gave a talk here, I think a few years ago on these, so I highly recommend watching his talk. It's great. Okay, so we've talked mostly about robots for the first part of this talk, and we've also focused on the setting of imitation, where there's in some sense some sort of idealized behavior we want the robot to reproduce. I now want to switch to a setting where it's much less clear what we want to do, where there's some sort of difficulty specifying the behavior we actually want. Furthermore, I'm also going to switch to the language modeling context for this part of the talk. And we're again going to focus on this translation of theory to practice. So in particular, we're going to focus on the setting of preference fine-tuning. So let's imagine there's some question we want our language model to answer, a prompt in NLP terms, and we're going to sample multiple answers to this question. The way we're going to do this is by generating a token, and then generating another token conditioned on it in an autoregressive fashion. And we can view the concatenation of these tokens as a completion. And we can imagine doing this multiple times. So we get multiple answers to the same question. We can then ask a person for which of these two answers to the question do they prefer. So maybe they prefer the top one to the bottom one. Then given this data, our goal is going to be to maximize the relative probability of generating psi1 over psi2. We don't want to just maximize the probability of generating psi1 because we don't know that psi1 is good. We just know that it's better than psi2. So mechanically, the way we do this is we train a reward model, aka a classifier, between these two things, and use it to provide supervision for a downstream reinforcement learning procedure. This is often called RL from human feedback, and it's part of the training pipeline of all today's most powerful foundation models, from OpenAI's models to the DeepSeek models to the Gemini models. So that said, when we do these sort of experiments in academia, and especially when we want to train smaller scale models, it's much more common, rather than asking a person for labels, to ask a powerful supervisor model for labels. And this is often called the LLM as a judge setting. So instead of having a person pick up which of these two completions to a prompt we prefer, we instead ask an LLM to pick between these two. Now, while this is a reasonable proxy for human judgment in certain situations, it also introduces complications because these language models often have conflicting and messy preferences. So let me walk through a toy example of this before trying to convince you this is a real problem. So let's imagine our language model is asked to rank 3 options, rock, paper, and scissors. And it tells us that rock is preferred to scissors, scissors is preferred to paper, and paper is preferred to rock. Now let's imagine trying to back out our reward function that explains these preferences. Well, it would need to simultaneously set the reward for rock higher than that of scissors, the reward of scissors higher than that of paper, and the reward of paper higher than that of rock, which is mathematically impossible. Right? And if there's no reward model that can fit this data, this also means there's no well-defined optimal policy for this problem. And more than being like a weird edge case, it turns out this is actually the norm when we get feedback from LLMs. So I'm going to plot results across 2 different tasks here. The first is instruction following. The second is multilingual reasoning. On the x-axis, I'm going to plot the number of completions we're going to ask our language model to order. So you can think of the rock, paper, scissors examples we just walked through as being 3 because there's rock, paper, and scissors. And on the y-axis, I'm going to plot the proportion of prompts on which we see these sort of conflicting preferences, in which case you're not able to actually order things. And what we see is that if I ask you to just order 8 completions, so I make your batch size 8, your language model already on nearly 100% of prompts will not actually be able to order these consistently. This is not really an edge case, it's actually the norm we actually see in practice. So when we have these sort of conflicting preferences, there's no optimal policy that always wins. There's nothing that always generates the most favorable completion, because there's no single most favorable completion. But there is a policy that is the hardest to beat. There is a policy that generates an unfavorable completion as infrequently as possible. So you might guess that for these sort of rock, paper, scissors examples, it's a policy that generates rock 1/3 of the time, scissors 1/3 of the time, and paper 1/3 of the time. So this is in some sense a more robust solution concept. More formally, this is an idea called a minimax winner, which has deep roots in the social choice theory literature and is also connected to a bunch of the really excellent work in pluralistic alignment that's been coming out of UW. But more formally, what this really looks like is I want to find some policy, pi1, that when I judge it against its worst case comparator, pi2, generates completions that are preferred as often as possible. Where I'm using p, pi1, pi2, I'm sort of abusing notation here to take an expectation over completion psi1 and psi2 drawn from the policy for the same prompt. And the high-level takeaway you should have from this math is that this is robust to conflicting preferences, that I'm treating the preferences as an object rather than trying to back out some sort of underlying reward function that has to be able to rationalize them. So while this approach has a long history in the social choice theory literature and has nice theoretical properties, it's pretty hard to actually do. And this is for the simple fact that adversarial training is hard. So imagine what it would take to actually do the algorithm or compute the thing I just described, right? I'd have to take a min over language models, I'd have to take a max over language models, and I have to ask a third language model for preferences, right? This is actually really quite computationally challenging to do at scale. So while these approaches, had a rich history in the social choice theory literature, actually applying them to the setting of language model fine-tuning wasn't a thing we were able to do until recently. I now want to talk about how we were able to do that, and it's going to boil down to this idea of being able to use self-play to compute minimax winners. So I'm going to leverage a simple insight here, which is that the probability of preferring orange over red is going to be equal to 1 minus the probability preferring red over orange. And this is really just axiom probability, right? The probability of an event is 1 minus the probability of the complement of the event. But the simple observation lets us do something kind of cool. So let's bring in back the game from earlier and focus on just the inner problem. So I'm going to apply the equality we just described and get 1 minus the probability, the preference probability of red over orange. Then what I'm going to do is swap the max for a min and drop the negative sign. And if you look at this optimization problem here, you'll notice it's symmetric to the one the outer player needed to solve. What this means is that rather than actually having two models and train them adversarially, we can instead have a single model and compare its completions to its own last iterate. So I'm going to walk through what this means mechanically before formalizing this a bit. So practically what this means is that we take our language model, we sample multiple completions, so multiple answers to the question, and we ask our judge model for a pairwise preference between these two completions. So maybe it prefers the first one to the second one. We then use the win rate of each completion as a reward for a downstream reinforcement learning procedure. So because there's only two completions here, win rate's going to be 1 or 0, so psi1 is going to get reward 1, and psi2 is going to get reward 0. We're going to then use RL to update our policy. So a little bit more formally, we can use this as running T rounds of a no-regret policy optimization algorithm against a sequence of reward functions, where at each round, we define the value of a completion to be how often it's preferred to completions generated by the policy for that round. That's a little bit more formally what self-play means. We can then use this to update our policy. And if we do this for T rounds, the mixture of the T policies we compute will converge to an approximate minimax winner at the rate of the underlying no-regret algorithm. I'm happy to talk about these offline, but there's a bunch of nice extensions of this in theory to handle things like multi-dimensional preferences, the sort of rubric rewards that are very popular these days, coverage conditions for preference data for equilibrium computation, and gap-dependent fast rates under consistent preferences. But for now, though, I want to talk about how we actually use these algorithms to do something I think is very important, which is give language models the ability to reason in lower resource languages. So if we look at the distribution of text on the internet, roughly half of it is in English. There's like 6% that's in Spanish, German, Japanese, French, and then 20% is all other languages on the internet, including, for example, my family's native language. And this means that when you ask a language model a question in one of these other languages, you often get a much worse answer than if you ask them the same question in English. So the problem of actually solving this is that we actually don't have enough data on the internet to actually train a model to reason in these lower resource languages. This potentially introduces opportunity for us to sample multiple completions from our model and ask a judge to give us feedback and actually train a model to reason in this lower resource language. Now, I think the most natural question you might have at this point is like, well, if my judge also didn't see much data in one of these target languages, how is it supposed to judge well, right? So the way we're going to get around this is we're going to provide an English reference as privileged information to the LLM judge. So rather than having to do judgment in the abstract, we're merely going to ask it to say which of these two completions in a particular target language is a better translation of this reference. So this is essentially reducing the complexity of what the judge needs to do to make its judgments more accurate. And when we actually run this algorithm, we're able to learn a lot more, even with a limited amount of data. So I'm going to plot two different metrics for you here. On the y-axis, I'm going to plot the accuracy. So these are all math questions. So it's the performance, the accuracy of the final answer in terms of whether you got it right or wrong. On the x-axis, I'm going to plot the percentage of the response that's in a target language. So in these things, we have both a reasoning chain and a final answer. And I would argue that if we want these models to be useful for people who speak a particular target language, we want these responses to be in a language they actually understand. And we're going to compare four models. The base Quen series models, models trained via supervised fine-tuning in blue, models trained via our algorithm in orange, and models trained by the Quen team with significantly more data in purple. And we'll see in low resource languages like Swahili, we're able to significantly outperform fully post-trained models on both axes, Pareto dominating them, even though they had access to much more data. And as we increase how much text there is on the internet of each of these languages, we will see continual Pareto dominance until we get to particularly high resource languages like Spanish, where we do slightly worse, but we still do comparable even though we had significantly less training data. And also, rather than doing individual language training, we can actually do cross-lingual training across a bunch of different languages. And here I'm averaging results across a bunch of different languages. And we see we're able to Pareto dominate the Quen series with 1/8 that much training data in terms of both the percentage of the response that's in the target language, as well as the accuracy of answering these questions. So maybe your takeaway from this part of the talk should be that these sort of self-play algorithms are robust to sort of conflicting feedback we often get from LLM judges, and this has practical implications for us learning from conflicting foundation model feedback. I also want to note in terms of broader impacts of this stuff, some friends down at MSR Run use these algorithms to train language models at scale. And it turns out that at the time of release, these were the top 7 billion parameter models on Chatbot Arena. This is probably not true anymore given how fast these results change, but I think that's still pretty cool. So for the last part of my talk, I want to drill a little bit more deeply into why reinforcement learning allows us to learn more from less. So rather than working from theory to practice, here I'm going to do something a little bit more like an empirical science and go from practice and try to back out theory that explains it. And this is all based on a recent iClear paper of ours. So if we abstract away a bunch of details, what have we talked about from this talk, right? We started with some data for demonstrations for the first part of the talk, preferences for the second part of the talk. And then there were these supervised learning approaches that directly learn the policy from this data. So in the imitation context, this was behavior cloning. In the preference learning context, this is DPO, direct preference optimization. Don't worry if you haven't heard of these algorithms, they're really just classification and regression. In contrast, the approaches we talked about today mostly have a two-step procedure. So first we learn some sort of reward function via supervised learning, before then learning a policy via reinforcement learning. And I want to note that beyond the experiments I've shown you here today, this is a widely deployed paradigm from OpenAI's models to the Gemini models to the DeepSeek models. And if you stare at this picture for long enough, you'll probably notice a few concerning things about it, like I did. The first thing you might notice is that this first step here loses information, right? We start with the raw data, and in some sense we compress it and throw things out to get a reward model. Then the second step here can't create any new human data, right? We just have the reward model we learn, right? We're just sampling from our model in reinforcement learning. This is also a really hard optimization problem, right? This is a hard, challenging RL problem. But it's actually really weird that this two-step process is working better than the one-step process, right? And a little bit more formally, the data processing inequality tells us that this detour through a reward model can only lose information and can't create anything new. So for the last part of my talk, I want to drill down on why does reinforcement learning learn more from less? What is it about this detour that actually improves performance? So this is a hard question. There's a bunch of different moving parts here. So I want to start off with something easier, which is when should this detour do nothing? Like when should the picture look like this, where the two-step procedure and the one-step procedure give us the same policy? And informally speaking, if a set of policies and reward models are isomorphic to each other and there's no optimization error, these will lead to the same solution. So intuitively, the reason this is true is if pi and r are the same class, this means that pi hat RL and r hat are the same point, and the second step doesn't move you. I'm happy to be more precise about what I mean by this offline if anyone's curious. But okay, let's try it out. Let's do controlled experiments where we try to get as close as possible to this isomorphic classes setting. So I'm going to use the same architecture and base model to train all policies and reward models for this. I'm going to use the same data set to train both the offline policy and the reward model we use for online RL. So all methods get access to the same amount of human information. I'm going to use the same optimizer and loss function to train both the offline and online RL policies. So here, oftentimes when people compare offline and online algorithms, they use different optimization algorithms. I'm trying to eliminate that confounder here. So it's hard to have perfect optimization in practice, but I can have equally imperfect optimization. And for this part of the talk, I'm going to use purple to refer to the supervised learning approaches, and orange to refer to the two-stage approaches that first learn a reward model before backing out a policy via reinforcement learning. So what we see in practice is, in contrast to what we would predict in theory, even in this isomorphic classes setting, we still see the offline algorithms underperform the online algorithms. So when I plot results on a summarization task across two different sizes of models, 1.4 billion and 2.8 billion. And what we see is the supervised learning approaches are able to improve performance on top of the base policy, but the online algorithms that have access to the same information, same amount of human preferences, are still able to improve performance even more so than this. So the high-level takeaway you should have from these plots is that we're seeing a gap between what the theory would predict, that the orange bar and the purple bars will be the same height, and what we actually see, which is that the orange bars, the interactive algorithms, do better. So there's a bunch of different explanations you could come up for why this is the case. And I spent roughly 2 years of my life coming up with different explanations here. So maybe the first one you might come up with is, okay, is there some sort of intrinsic value in online data? So can we actually get some sort of new information during sampling, right? I would say we can't create something from nothing, right? I can't get any new ground truth human preferences during this process, right? And this is in contrast to the usual RL setting where I actually have a ground truth reward function that is giving me new information when I'm interacting with the environment. Here, our reward labels are just made up by our reward model. They're just imputed, right? The second thing you might predict is there's some sort of failure of offline regularization to the reference policy. So you might say that maybe the online algorithms are able to better control the divergence between your starting policy and your final policy. And this is true for a lot of different RL algorithms. But for my experiments, I use the same regularizer and the same optimizer for everything. So that can actually explain the results I showed you here. Another hypothesis you might have is that reward models can be trained on wider data sets. So if you look at the reward models that are top of all leaderboards, you'll see they're trained on far wider data sets than you'd want to train a policy. But it turns out you can ablate this away and you still won't see, you still see a gap. So we considered a lot of other alternative hypotheses. I'm happy to walk through them offline if anyone's curious. But for now, I just want to drill down on the one hypothesis that was able to predict all the experimental results these weren't able to, as well as make new testable predictions about new phenomena. And that is this idea of generation verification gaps, that for many problems in computer science, they're easier to check than to solve. The canonical example of this is the Sudoku puzzle in my head. So to check a Sudoku puzzle, I just need to check every row, every column, and every 3x3 grid cell. But to solve a Sudoku puzzle, I need to do this sort of combinatorial search over every kind of possible way to complete the puzzle, right? A little bit more formally, you can think of GB gaps as problems that are in NP but not P. And if you, like most computer scientists, believe P is not equal to NP, you must believe some such problems exist. I haven't yet tried to convince you that real problems have this flavor, but some such problems must exist. So if we have a generation verification gap, the picture we've been sort of building for this entire talk is a little bit incomplete. The first thing we're going to do is identify that policies are really generators and rewards are really verifiers. So the supervised learning approaches are trying to directly learn a generator over the full class of policies. In contrast, if we look at the two-step approaches, we can think of there inside the full class of reward models, there being a smaller set of relatively simple reward models. I say relatively simple here because there's a gap between the complexity of verification and generation. And then on the flip side, we can think of there being a set of policies that are optimal for relatively simple verifiers. Then the first step of RL is finding one of these relatively simple verifiers. The second step is computing its optimal policy. However, this means end-to-end, we're only looking over policies that are optimal for relatively simple verifiers rather than the full set of policies. And because we're searching over a smaller class of functions, a standard statistical learning argument would tell us that we need less data to solve this problem. So slightly more formally, we can prove that reward modeling plus RL is doing maximum likelihood estimation over this constrained class rather than the full set of policies. And this provides a statistical separation between online and offline algorithms here. There's also some really nice interpretations of these ideas in terms of computational and statistical trade-offs, and I'm happy to talk about that offline if anyone's curious. But for now, I think there's two things I have to still do. The first, I have to convince you that this picture is not pretty, it's actually what's happening in practice. And second, I have to do it to use this hypothesis to make a new testable prediction rather than just confirming old empirical results. So I'm going to do both of these things now. So to give you some evidence of a generation verification gap, I'm going to scale the relative size of policies and reward models. So I'm going to compare three sizes of models, relatively small 1.4 billion parameter up to relatively large 6.9 billion parameter models. And I'm going to show that when I generate from a relatively large 6.9 billion parameter model, we see the same performance across all three sizes of word models. What I'm plotting here on the y-axis is the best of n performance, so essentially how well these models rank samples. And you see the same thing through when I generate from a relatively small model. So your high-level takeaway from these plots should be that using a much smaller word model than your policy doesn't hurt, and using a much larger word model than your policy doesn't help. So this means, in some sense, a smaller function class, a smaller network, is able to actually capture this function. And this provides some intuition, or some evidence, I should say, that rewards are simpler than policies, because it can be captured by a smaller network. Now, I'm also going to try and make a testable prediction here, which is that if there is no generation verification gap, the offline and the online algorithm should get the same performance, matching the picture from information theory we had earlier. I'm going to do this in two ways. The first way I'm going to do it is simplify our policy. The way I'm going to do this is reduce the planning horizon of our problem. So rather than generating a full summary for an article, I'm going to ask it to generate like a 2-word summary for an article. And for these problems, there's not really much of a complexity between generation and verification because it's just a one-step problem. The other way I'm going to do this is I'm going to complicate the reward function. So I'm essentially going to make the reward function be something like a lookup table, a very complicated function. It takes a lot of data to learn. And what we see across these two tasks is that much closer than before, maybe not exactly, but much closer than before, we see the offline and the online algorithm's performance essentially collapse. So your takeaway from these plots should be that we match the picture in information theory that the offline supervised learning algorithms and the online RM plus RL algorithms achieve the same performance when we don't have this sort of underlying generation verification gap. I'd also like to note that maybe a natural question you might have at this point is like, well, what if I wanted to widen the generation verification gap? And I would sort of argue that that's what we've been doing empirically for this whole talk. So for example, in the robotics context, what we did is we had videos and we put them into natural language. And this really simplified the verification task for a VLM, given it's been trained on way more language data than vision data. Similarly, in the language modeling context, to simplify the task of judgment for our judge, we gave it access to this privileged information. This again made the verification task easier, widening this generation verification gap. So I have widening in quotes here because I don't mean this in any sort of like formal sense, but intuitively I believe this is aligned with the spirit of what I've been talking about for this part of the talk. So your takeaway from this part of the talk should be that RL allows us to learn more from less due to generation verification gaps. Now, I don't want to overclaim here. In science, you're never right, just not yet wrong. So I think there's a lot of other factors here at play, but I do think this does put this sort of separation and being able to learn more from less on solid statistical foundations. Yeah?
Are there bones where this is flipped, where the generator is simpler than the verifier?
It's a good question. I think maybe in terms of specifying the generator or writing it down, this might be true, but in a formal sense, it's hard for me to think of when this could be true. There are settings when they're the same. So in addition to the example I presented at the end here, imagine I ask you to do a really hard math problem, but then I hash the answer at the end. Then to check this thing, I actually have to solve the math problem and hash it. So I think the same is true. It's hard for me to think of an example where it's actually flipped in general. Yeah. OK. So while I think these techniques are promising, I think they're still a ways off from allowing us to be able to create the sort of agents I really want. So for example, something like a robot that can cook a 3 Michelin-starred meal rather than just core an apple, or a language model that can teach me to write a novel like Nabokov rather than just answering questions about one of his. So when I think about what it will take for us to get towards the agents of tomorrow, I firmly believe we need techniques that allow us to learn even more from less. And there's 3 ways of doing this that I am particularly excited about. So the first is training long horizon world models that would allow robots to learn to execute long sequences of behavior without the safety constraints of real-world interaction. So if we bring in our world models, our learned simulators from earlier, you'll notice that the videos I have here are like just 1 second long, right? So this is okay for reactive planning, but if I want to be able to learn to unpack my entire house, this is very hard to do inside this sort of simulator. And I think this is because we train these models to essentially predict the pixels that you'll observe after executing a sequence of actions. So instead, I imagine merely me having to predict a sufficient statistic for downstream decision making, an easier task, which would reduce the amount of data we need to train these models. I also think there's some deep connection between these ideas and the theory of decision calibration I'm happy to get into offline. Second is training long horizon verifier agents that will be able to look through long streams of experience, remembering what matters and forgetting what doesn't. So I had Claude generate this short story. It's pretty good, but there's a plot hole in it that I've highlighted for you in red here. I envision a verifier agent that could do the same thing and more, like check an entire novel for plot holes or code bases for bugs without having to read everything into context. I believe we could then use these verifier agents to supervise the training of more powerful models, providing a path to scalable oversight with less human supervision. And I think there's deep connection between these ideas and the theory of interactive proof systems that I'd love to get into offline if anyone's curious. The last thing I'm interested in is understanding the effect of supervised learning on downstream reinforcement learning. So in contrast to sort of like dichotomy I've presented for most of the day, the way we train foundation models in practice is we first have an offline supervised learning pre-training phase, which is then followed by an interactive RL phase. However, there's very limited understanding of what we should do offline to make online RL easier. So I'm interested in algorithms, for example, optimize the distribution of pre-trained data in the context of making downstream fine-tuning more effective. And I think there's a deep connection between these ideas and the notion of coverage in offline RL. And if we were able to make progress on a more semantically meaningful notion of coverage, this will allow us to do more semantically meaningful exploration, and that opens up a bunch of new possibilities. So to conclude, I'd like to thank all of my collaborators. They're one of the main reasons I love what I do so much. And if these ideas sound interesting to you, I'd love to collaborate with you as well. And yeah, I'm happy to take any questions you have. Thank you.
We have some time. Questions?
You hinted at that, so this is the complexity of generation versus verification, and also the relationship.
And also the relationship to, so maybe repeat that, generation versus verification, and then the relationship about for which of these pieces do you have more training data, right? Because that's why we might use video world models, because we have these huge data sets and things like that. And ultimately, they both play a really important role. Where do you think, like, over the next few years, we're going to see more coming out of it by choosing the right kind of data sets for the right kind of subtasks in the pre-training realm, or by picking the right kind of algorithms for doing that training?
That's a good question. So broadly speaking, I view compute as scaling faster than data. So I think we're going to see more and more benefit of more complex algorithms as time goes on. And in particular, I think algorithms allow us to actually pick which data we use during pre-training are going to be especially important. Does that kind of get at your question?
Yeah, it's really, yeah.
Thanks, great talk. So I want to ask something about the first bit you presented. So as far as I understand, you're trying to match state action distributions for an expert, and that reduces the explosion you would get otherwise from like a global exploration. And you said it's primarily applicable to robotics applications. I'm curious if there are cases where that breaks down even for those applications. Let's say if you have maybe extremely long horizon tasks, or where the expert isn't really reliable. I'm just curious to understand limitations.
Great question. There's definitely limitations. So I think that if there's really, really long horizon tasks, right, what you could imagine happening is I don't want to do this whole backwards in time thing, right? So there exist randomized versions of this algorithm. You essentially pick a random kind of step to roll into, and then complete the rest of the episode. So that deals with maybe some of the horizon explosion. Maybe in terms of more fundamental limitations, though, I think there's often settings in which you don't have access to a large amount of expert data. And maybe you can use this for learning a verifier, but maybe you don't have enough to learn a good world model, or have enough for a good reset distribution. So that's where I think a lot of suboptimal data, multitask data, other things can be really useful there. So you maybe don't want to stick that directly into your policy because it's not doing exactly what you want, but you can use it to essentially allow your agent to know that there are consequences if you do the wrong thing and to recover from like slightly off distribution states. So in particular, I think one of the kind of core challenges in imitation is trying to imitate an expert when you can't perfectly reproduce their behavior. And if I essentially only reset you to states along a tightrope, this might be useful if you can't perfectly do what the expert does, but if you can't walk on the tightrope, this might not be particularly useful. So sort of widening that reset distribution with suboptimal data can be quite useful. And if you want to do this in simulation, you then need to use that data also to train your world model.
Thank you for the great talk. I was wondering on the future section where you mentioned about the long horizon world models. I was curious, like, what ideas you have there. Like, are you thinking of in terms of like abstractions to have that will enable this like long horizon rollouts, or is it something on the end of like, basically what kind of abstractions are you thinking of to enable these long horizon rollouts?
Good question. So I guess broadly I've been thinking about it from the level of representation learning. So there's some sense in which, right, if I have my latent state, it has to be able to reconstruct arbitrary pixels of my downstream image. This is asking for a lot, and this requires a lot of data to learn. But if instead I could be able to predict the downstream consequences of different actions, so more formally be able to predict Q values for different things my policy would want to do under different reward functions, I think this is both minimal and sufficient for this. I also think another thing I would want in these representations is, rather than being information theoretically sufficient, in the sense that there is a policy that can take this and do good things, there is a relatively simple policy that can take this representation and do things well. So there's some notion of like computational complexity of your policy that I think also should be factored into representation learning. So you have representations that are easy to learn on top of.
Any last questions? Okay, let's thank Gokul.